In this video, we will learn about the eigenvalues and eigenvectors with an example. So the definition is, given a square matrix A, if it is possible to find a vector V which is not equal to 0. By vector, what we mean, a matrix having only one row or column is called a vector. And a scalar such that this relationship holds, that means square matrix times this vector is equal to C times I times V. Okay, this small c is called the characteristic root, or we call it latent root or eigenvalue. I is the identity matrix, and V is, of course, it is called the characteristic vector or latent vector or eigenvector. Okay, now given this relationship, if we transpose this term to LHS, so it will become A minus Civ is equal to 0. Taking V common, so we will be left with A minus Ci times V is equal to 0 here. Okay, now this A minus Ci is called the characteristic matrix of this square matrix. Okay, so A minus Ci. Now since we have assumed that V should not be equal to 0, then that means the determinant of this characteristic matrix should be equal to 0. Okay, now when this happens, there will be infinite number of solutions for V, because we have assumed V should not be equal to 0. This term should be equal to 0. So for different values of V, we will get, infinite number of solutions for V. Now to force a unique solution, what we set a condition, or we normalize the solution by requiring that the sum of elements of the column vector this vector should be equal to 1. Rather, the sum of the squares of the vector V should be equal to 1, to force a unique solution. Otherwise, we will be having infinite number of solutions. Now, let's take an example to understand it better. Let us say we are being given a vector, and let me write it here. Sorry, a matrix, square matrix. Let us say we have minus 6, 3, 3, minus 6. This is our square matrix. We are told to find out the scalar, what we call, as I have told you, this scalar is called eigenvalue. Okay, let us say we are being told to find eigenvalue, and eigenvector. Okay, let us first try to find out the eigenvalue first. Okay, so let's write it here. How do we find out the eigenvalue? Okay, so first thing is, we form this matrix A minus Ci, and let me write it here. A minus Ci will be equal to, so A is this minus 6, 3, 3 minus 6. Then we have minus this scalar C times I. I is the, identity matrix 1, 0, 0, 1. Okay, first we find out this A minus Ci. So it will become, it is minus 6, 3, 3 minus 6, minus multiplying this constant to each of these terms. So it will become C, 0, 0, C. Okay. Now to find the solution, what will we do? We will set this, the determinant of this matrix, or let's further solve it. It will become, and let us write it here. So our A minus Ci came out to be, now subtracting this matrix from this square matrix, so we will have minus 6 minus C, then we have 3 minus 0, 3 minus 0, here we have 3 minus 0 again, 3 minus 0, which is 3, and I will not write it here, okay, to save the space. So 3 minus 0 is 0, so again we have minus 6 minus C. This is our A minus Ci matrix, what we call the characteristic matrix. Now what we do for getting the eigenvalue, we set the determinant of this matrix, and let's write it here. A minus Ci. We take the determinant of this matrix and set it equal to 0. So taking determinant meaning multiplying these two elements first. Okay, that means we have minus 6 minus C. To this we multiply minus 6 minus C. Okay, multiplying these two, then subtracting and multiplying these two elements, that is 3 times 3, and we set it equal to 0. Solving this will give us C square plus 12C plus 27 is equal to 0. When we solve this, it will come out to be, by factorization, it will come out to be, I am just trying to save the space here, C plus 9 times C plus 3 is equal to 0. That means we get two values for C. Okay, either let us say C is equal to, or let's write here C plus 9 is equal to 0, which means C is equal to minus 9 when C plus 3 is equal to 0, which gives us C is equal to minus 3. Okay, so we got two values for C, and let us say they are C1 and C2. Okay, so we got two eigenvalues, so we can say we got two eigenvalues, that is minus 9 and minus 3. Now next is to find out the eigenvector. So let me write it here, eigenvector. How do we find out the eigenvector? What will we do? We will put one characteristic root or one eigenvalue first. Okay, so let us put C1 is equal to minus 9. We put the value of C1, as we know here C1 is equal to C1, and this also C is equal to C2. Put the value of C1 is equal to sorry, minus 9 in this matrix. Okay, rather in this relationship. Let me write it here. What is the relationship? A minus Ci times V should be equal to 0. We put the value of C1 is equal to minus 9 in this matrix. The value of this is this matrix. So we have A minus Ci is equal to, it is minus 6. Then we have minus, so in place of C we have C1 which is equal to minus 9. So minus into minus is plus, so we will write plus 9. Then we have again 3 here 3. So 6 minus into minus is again plus 9. Okay, so A minus Ci is this. To this we multiply the vector, that is V1 V2, which is the column vector, and we set it equal to 0. Okay, when we do this thing, what happens? Let us further solve it. So solving this, we will get 3 3 3 3 times V1 V2 is equal to 0. Okay, since the coefficient matrix is linearly dependent here, so it is capable of infinite number of solutions. So the product of the matrix gives us two equations which are identical. That is, we will get, if I multiply this matrix with this column vector, I will get 3v1 plus 3v2 is equal to 0. Again, we will get the same two identical equations. Now let us write 3v2 is equal to minus 3v1. Okay, 3v1. So cancelling 3 on both sides, we will get v2 is equal to minus v1. Okay, so this v2 is equal to minus v1. As I have told you, we will get infinite number of solutions here. To get rid of this, we will normalize. Okay, we will normalize the solution in such a way, as I have told you, to get a unique solution, the sum of squares of this vector must sum up equal to 1. That means v1 square plus v2 square should be equal to 0. Sorry, 1. So v1 square, let's write v1 square. What we got here, plus what is v2? V2 is equal to minus v1 square. So we have minus v1 square. It should be equal to, sorry, it is equal to 1. So this gives us v1 square, square of a negative number, negative term is always positive, plus v1 square is equal to 1, which implies twice v1 square is equal to 1, which gives us v1 square is equal to 1 upon 2, 1 upon 2, which implies v1 is equal to, let's take only the positive root here. That means we will get v1 is equal to 1 upon 2, okay, under root 1 upon 2. And also we know that v2 is equal to minus v1. That means our v2 will be equal to minus v1. So we will have minus under root 1 upon 2. That means eigenvector, we got two values, that is v1, or our eigenvector came out to be, which is v is equal to v1 v2, which is equal to, so we got two values, that is under root 1 upon 2 and minus under root 1 upon 2. Okay, this is the first eigenvector. With the same method we can find out the second eigenvector. How? This time we will put the value of c1 or rather we will put c2 is equal to minus 3. Okay, so we put here c2 is equal to minus 3 and solve it accordingly. And let me show it here. If I have, okay, let's solve for second characteristic root also. So this time we said c2 is equal to minus 3, okay, forming this matrix, that is A minus ci times v is equal to 0. So this matrix is this minus c minus 6, so minus into minus will be plus. In place of c we will have c2, which is equal to 3, so we will get 3 here. Then we have 3 minus 6 plus 3. Okay, to this we multiply the vector, which is v1 v2 is equal to 0. So we will get here minus 3. Okay, so we will get minus 3 minus 3 v1 v2 is equal to 0. Again we will get two identical equations when we multiply, that is minus 3 v1 plus 3 v2 is equal to 0, which gives us 3 v2 is equal to 3 v1. So v2 is equal to v1. Okay, getting this, to normalize, to get rid of the infinite solutions, we normalize the solution in such a manner that the sum of the squares of the elements of this v column vector should be equal to 1, that is v1 square plus v2 square should be equal to 1. So we have v1 square, v2 is equal to v1, so in place of v2 square we have again v1 square, which is equal to 1, twice v1 square is equal to 1, or v1 is equal to 1 upon 2, which gives us v1 is equal to, let's take positive root here, 1 upon 2 only. Okay, so v1 is equal to under root 1 upon 2. That gives us, v2 will be also equal to, because v2 is equal to v1, we will get also 1 upon 2. That means our second eigenvector will be v1 v2, which is equal to under root 1 upon 2 under root 1 upon 2. So we got two eigen vectors here. I hope I make myself clear in this video. Thank you.